So, welcome to this particular lecture, and we will continue our discussion what we have been doing so far. Now, the decomposition of a shape. So, there are different ways, multiple ways one can do that. So, let us start with, let us have this cell connected, which is, let us look at this picture. So, this is a approach called minimum correction approach. So, this is for the decomposition of a shape through minimum correction method or approach. So, you have these 2 points or the cell center connected along the line DCF. This is the E unit vector E along this surface point. This is the direction of the surface vector. Then we got 2 components. Now, in this case, the idea is that the way it is done to keep the non-orthogonal correction. So, the non-orthogonal corrections or the contribution for the non-orthogonal distribution is as small as possible. So, that is why we call it a minimum correction approach. So, that means the contribution due to, so SF will have 2 components, one is EF, one is TF. This is like an orthogonal contribution, this is our non-orthogonal contribution. So, idea is that you sort of minimize TF contribution as much as possible, okay. And but what happens if non-orthogonality increases? Non-orthogonality increases. If that increases, so the contribution to the diffusion flux from phi f and phi c, this contribution will start decreasing, okay. Now, in this case it would be simple to compute the EF is E dot SF E, which is nothing but SF cos theta E. So, that is a simple way one can do that. Now, this is approach, one of the approach one can do that. Then one can do second way of doing that, that is called orthogonal correction approach. So, what you do here, again you get these particular 2 elements, they are connected as usual, and the component of the surface vector, one would be along this line if this is theta, and the other one would be along this line, the perpendicular one, okay. So, there also contribution comes from both phi f and phi c. So, here what you do, you define EF again SF E. So, that is our orthogonal corrections approach. Now, that is exactly like what kind of contribution that we take. It essentially keeps the contribution of the term involving phi f and phi c same as orthogonal mesh irrespective of the degree of non-orthogonality. So, this is why it is called the orthogonal correction approach. You just take a contribution like that where it will involve the information of these two cell centers as we have done for the orthogonal mesh irrespective of the degree of non-orthogonality. Once you do that, this may not be a very acceptable approach, because if your theta increases, this can create trouble. Now, another option, one can have the over relaxed approach. Okay. So, what you do here, the vectors and everything looks similar, the corrections vectors and the components. SF will have as usual EF plus TF, cell centers are connected along E through the surface. So, here the terms which are very important here is phi f and phi c. Now, how we do that, or mathematically one can achieve this calculation? We can get EF equals to SF by cos theta E, which is SF square divided by SF cos theta E. One can write SF dot SF divided by E dot SF E. So, to summarize what we are doing it here, the diffusion flux at an element face of non-orthogonal grid cannot be written solely in terms of the values which are connecting through the cell centers, or the nodes which are connecting through the cell centers. So, what it require? A term which will account for this non-orthogonality. So, you need a term which will account for the non-orthogonality or this sort of angle theta. So, that is the degree of the degree of non-orthogonality. So, the term which accounts for the non-orthogonality needs to be added, and which is called the so called cross diffusion term. So, that is very important term for non-orthogonal grid system. So, if we put together everything what we have looked at it, then one can see that what we are doing is at the gradient calculation at the faces. So, this was the component. So, this del f by f dot SF minus EF. So, we are trying to see the contribution from the cross diffusion term, which was essentially one is that del f phi dot n minus cos theta E SF. This was the case when you have minimum correction. Then another option is that del phi f dot n minus E SF, which is normal correction, and the last option, that is that del phi f dot n minus 1 by cos theta E SF. So, this is over relaxed. So, theoretically what we are doing it, we know the surface vector, or the surface vector will have two component. Now, the component which is going along the line that connecting the cell centers, that is along E or the norma, that is easy to obtain, and then that involves the information of phi c and phi f, and once you obtain that information, then you can actually, using this information of the vector algebra, we get the contribution from the cross diffusion term. So, instead of going directly to calculate delta dot, so if you go back and see, there are two components for my flux discretization. One is like our orthogonal contribution, which can be directly computed using the information of the connecting cells and the distance connecting between these two cell centers, and then there is a contribution which comes from the cross diffusion term. Now, this cross diffusion term, instead of calculating directly, what we do, we calculate the corrections for EF, and then using that EF we get back the other component. So, what happens is that, as we said, the cross diffusion component, this component, it is absolutely 0 for orthogonal system. So, that actually brings back the non-orthogonal system to be a orthogonal system, or the behavior of the non-orthogonal system when you assign this cross diffusion term to be 0, that becomes an orthogonal system. Now, the things come, how do we treat this cross diffusion term? That is a very important issue, because this cross diffusion term cannot be, so if you look at it, the cross diffusion term, they cannot be, actually this cross diffusion term cannot be expressed using the nodal values. So, the point here is that when you calculate this component along E, or the sort of pseudo orthogonal component, you can use the information of these two cell or the information of these nodal values and can find out that EF, but or delta phi dot EF. But cross diffusion term, the problem arises, this cannot be straight away expressed through the nodal values. So, due to this some kind of corrections approach is required and some sort of an calculation is required. One of these, that how do you calculate the, essentially we can look at it, the first the gradient computation, and then we will see in an orthogonal system how do we actually derive this cross diffusion term. So, gradient computation, so the point here is that in non-orthogonal domain, as we have already come across, the non-orthogonal domain, the computation of the diffusion flux itself is complex, because it cannot be linearized, and so the diffusion flux cannot be linearized in a straight cut way or straightforward way, and also cannot be written directly with the function of nodal values. So, that means the non-orthogonal system gives rise to some sort of a challenge for the engineers or the scientists to get this computation done in a perfect fashion. So, which on the other way around, it means the gradient calculation or the gradient has to be evaluated in order to incorporate is non-orthogonal contribution in the discretization system. So, essentially my discretized system must have the information of non-orthogonality. So, which gives rise to the cross diffusion term, and the cross diffusion term cannot be calculated using nodal value. So, that is where the problem lies. So, what we can use for calculating the flux, actually we can use some gradient theorem. If we use the gradient theorem, what it gives you, that which we have done, del phi dV is the surface integral of phi ds, okay, and this is actually the ds is outward pointing interfacial vector or you can say outward pointing surface vector. Okay. So, what one can get the average gradient, how do you got it, del phi v, the average gradient we got the del phi dV. Now, once you combine these two, what you get for a system, that del phi c average value is 1 by V c surface integral phi f s f. Okay. So, once you integrate over the self faces, this will lead to 1 by V c summation n b c phi f s f. Now, what one can do, the gradient at the face can have two contribution, one is G c delta phi c plus G f delta phi f, where phi c phi f are the nodal or cell center values. So, you use the information of the cell center values to get this particular information. Now, once we use the cell center value, and then we can sort of linearize the system using the information of that. Now, if you look at the whole summation term over the cell, so which is essentially J f for the diffusion term S f. Now, this term is going over all the faces minus gamma del phi f dot E f plus T f. So, this comes, as we have seen, this will be a two component, one is E f, one is T f, and this is giving rise to cross diffusion term, or rather non orthogonal correction term. This is my sort of orthogonal correction term. Okay. Once we do that, then I can write this one expanding, and I will write this one as minus gamma del phi f dot E f plus summation over all the faces minus gamma del phi f dot T f. Okay. So, what it does, this is a term, this term is 1 and this is the second term, term 2. Term 1 is the orthogonal linearized part or contribution, or term 2 is due to non orthogonal linearized part. Okay. So, we get two different contribution as expected. Now, if you expand it further, so this would be over f. If I write down, this would get me back that minus gamma f EF phi f minus phi c by d Cf plus summation over all the faces, and we get minus gamma del phi f dot Tf. So, we retain the second term as it is for the time being. Then we again simplify the first part, and what we get is that gamma f df phi c minus phi f plus over the all the faces we retain gamma del phi f dot Tf. Here the df is the again the similarly as we have defined for the orthogonal system, it is the geometric diffusion coefficient, which would be Ef divided by dCf. So, that is the definition of df. Now, if you take it slightly more or expand it slightly more, so what we are having at the left hand side is the flux going for all the faces, and after decomposition or expanding we get now summation over all the faces, it is flux Cf phi c plus summation over all the faces flux Ff phi f, okay. And so this you can put in the bracket plus summation of f going over c, you have flux Vf. So, all these things are written in this coefficient format, what we used to do for the orthogonal system. Here once you write down this, if you expand these things, now if you expand and these things, the final form of my discretized equation would be like phi c a c plus summation f going over n b c a f phi a b c. Again here f stands for elements or rather neighboring elements. Okay. So, where you get all this information. So, if you look the discretized system, they look exactly similar to our orthogonal system. And again I am repeating or reiterating the fact, this is one of the beauty of the finite volume method, that what you get at the end the discretized equation, or rather this is my sort of discretized equation. So, whether it is a orthogonal system or non-orthogonal system, the discretized equation looks pretty similar. So, mathematically they look similar, only differences will come in these coefficients. So, what that makes you to do or allow you to do that you can have a discretization pattern or discretized equation which looks similar and can be applied to all sort of system, then it is much easier for computing purposes. Now, before we talk about that in more, we just look at the coefficients here for this case, which is going to be now flux Ff, which is nothing but gamma f df, and my Bc is Qc Bc minus summation of NBC flux Vf equals to Qc Bc plus summation of f these things to gamma delta phi f dot Tf. So, this is the contribution which come as a source term in the non-ortho, this is cross diffusion term. So, as I was mentioning, the discretized equation looks exactly same for your orthogonal or non-orthogonal system. It starts, so you can be on a one single framework and then one can do the programming, and that is the advantage of finite volume method, that it actually gets you back a same system of equations which can be applied to both orthogonal and non-orthogonal system. Only thing is that what you need to take care of these coefficients. So, these coefficients are only going to change from one case to another case, and for non-orthogonal system you come across this cross diffusion term, which is a extra contribution come as a source term. If this term goes to 0, that will become the orthogonal system, and the other things will look exactly similar. So, that is where the advantage lies, that we can have a same discretized system for both orthogonal and non-orthogonal system and can be used with different coefficients. So, thank you. We will discuss other things in the next lecture.